You're listening to WeAreSTS, a podcast from the Department of Science and Technology Studies at University College London. Hi everybody, welcome to WeAreSTS and welcome to UCL. I'm your host, Professor Joe Kane. I wanted to start the new season with something exceptional. This episode is a particular favorite of mine. If you listen to anything in Season 1, you'll know that here in STS we run UCL's master's degree in Science Communication. One thing students have to do is a summer project that's either practical content or original research. One of the practical projects submitted last year was the podcast episode you're about to hear now. It was created by Mary Westover, and I think it's a cracker. Mary wanted to create something modeled on the podcast show Radiolab, and if you've never heard that work, just know it's excellent. I mean, it's top quality stuff. Mary wanted to make something that sounded as though they had made the product. She also used the opportunity to investigate a problem in physics that had been bugging her for a long time. What is dark matter? Put the two together and you end up with Mary's episode. She interviews some physicists, travels to a big lab stuffed inside a mountain in Italy, and, well, I'll let Mary explain everything herself. I hope you enjoy this episode as much as I did. I'll meet up with you again on the other side.
This is the Xenon experiments.
Wow.
It's the first one that built this transparent set.
So I'm inside this mountain in central Italy.
You just do science.
Yeah.
And you can imagine, since you are American.
I'm at the Laboratory Nazionale del Gran Sasso. It's in the mountains about 120 kilometers from Rome.
On the 5th Avenue in New York.
So the Xenon is in here.
And I came here to see this.
The
storage,
Xenon
okay.
experiment is in here.
Oh, okay.
The Xenon is in
An enormous tank where deep inside sits 6 tons of liquid xenon. Why am I so excited to see this? Well, I'm going to tell you, but first I have to tell you why this lab exists.
Cosmic rays that can affect our measurement. It's not sufficient. All the experiments here.
I'm Mary Westover,
No way!
and this is Perfect Science. Okay, so you know how when you're a kid and they teach you in school about phases of matter, solids, liquids, and gas? They tell you that matter makes up everything. You, me, all the other stuff around us. And then later on in school, they might teach you about mass and the force of gravity. All matter has mass, and because of gravity, all that mass has a certain weight. Gravity is the force that holds everything together. It's what allows the sun to hold all the planets in its orbit. It is what keeps us grounded to the earth. And we know exactly what the force of gravity is. We can calculate something's mass based on its gravitational pull. And we know exactly how strong gravity is. We can calculate something's mass based on how much gravitational force it has. And that math usually works out. But there's just one problem. So in 1933, this guy named Fritz Zwicky decided that he was going to add up all the mass in this cluster of galaxies. And he got a number. But the number he got didn't make any sense. It was too small. It wasn't enough mass to account for all of the gravitational pull these galaxies had. And when I say too small, I mean it was only 1% of what it needed to be. So he figured there must be other stuff out there with a gravitational pull. He called it missing matter. And this missing matter remained a mystery for the next 40 years, until a few other scientists observed a similar phenomenon and found that in any typical galaxy, the observable mass is not enough to keep the stars orbiting. This missing matter is now called dark matter. It's called this because it doesn't emit any light. In fact, it's totally invisible. And besides its gravitational pull, there's really no way we can observe that it's there at all. But after years and years and years of research, most physicists have agreed that about 98% of all the matter in the universe is dark matter. That means that all the stuff that we can feel, touch, see, detect, the stars, the planets, everything, that's only about 2% of all the mass there is. This includes the planets and the stars and the asteroids. However small you thought we were, make it smaller. Because we are nothing when it comes to the sheer quantity of dark matter. Now, if this seems made up, it's because it kind of is. You know, in the same way any scientific theory is made up. There is a lot of evidence supporting the existence of dark matter, but there's still no definitive proof. So far, there's nothing concrete that you could point to and say, this is dark matter, I've found it. So if we've yet to see it or detect it scientifically, then how do we even know dark matter is there? And it acts so much differently than baryonic matter. That's the regular matter that we can touch and see. And so if it is out there, what exactly makes it matter and not something else?
There is a level of debate around, whether or not dark matter is, is it some form of matter, or is it some kind of fundamental misunderstanding about our theory of gravity, general relativity, which is the sort of the foremost theory of gravity by Albert Einstein. The vast majority of physicists are in this camp, where we are almost positive that dark matter is a form of matter that we just haven't detected yet.
This guy you're hearing now is Joe.
Joe McLaughlin. I am currently a postdoctoral research fellow at University College London, working for the Lux-Zeppelin, or LZ, dark matter search experiment.
The Lux-Zeppelin experiment is based in South Dakota, but it's a collaboration between 30 institutes spanning all across the US, UK, Portugal, and South Korea. As part of this project, Joe is searching for dark matter, and there's a bunch of reasons why he believes it's out there, but the biggest one is the bullet cluster. It's these two clusters of galaxies that are colliding, and you can actually see this happening with a telescope in space.
The bullet cluster is a merger of two galaxy clusters. Now, contrary to what a lot of people think, most of the matter, if we're not including dark matter, most of the matter bound up in galaxies is actually in the form of intra-galaxy plasma, or gases and stuff like that that's kind of flying around. So that plasma, or that gaseous matter, behaves like a fluid. And what happens when you shoot two garden hoses at each other? I mean, things go spraying around, like water gets kind of like rammed up in the middle, starts behaving very chaotically. Basically, the same thing happens when you have these galaxy cluster mergers. So they come together, and then the intergalaxy plasma that's kind of around all of the galaxies gets rammed up in the middle. We actually call that ram pressure. So in that pressure, like in that state, there's actually a lot of these high energy collision between the atoms in the gas. So they get locked up in the middle for the most part, but then there's also a lot of excitation. And when those excited atoms relax back down to a ground state, they emit light, usually in the form of X-rays.
Now, this light isn't visible to us because compared to the stars, it's pretty dim, but you can look at an X-ray spectrum to see what's going on.
You can actually see a high intensity peak of X-ray emission coming from around, if you have one galaxy cluster all the way over to the right, and another one is all the way over to the left, the peaks are kind of coming a little bit to the right and a little bit to the left, basically because the gases are being locked up in the middle.
So what Joe is saying is that most of the matter involved in this collision is in the middle. That's where all the gas plasma stuff is. And that's where you see the most X-rays emitted. The highest peak is in the middle, where most of the matter is. So when looking at gravitational signatures, it should line up with the X-rays. there should be stronger gravitational signatures in the middle, where most of the matter is.
But that's not what we found when we looked at that particular, well, I mean, more than just that. That's not what we found in these galaxy cluster mergers. We found that most of the gravitationally interacting matter was staying with the stars, which is contrary to what we thought before in terms of like how much matter is locked up in stars versus how much is in this gas. So that was kind of seen as the smoking gun, that there has to be particle dark matter that's non-interacting, electrically neutral and non-interacting, so that it would go right along with the stars and end up exactly where the stars are, or the galaxies are. It's all but a confirmation in the eyes of most physicists that particle dark matter is probably the answer to what we're looking for. And when you're dealing with, with nature, like the concept of Occam's razor comes into play, which refers to the simplest and most elegant solution to a problem is most likely the correct one. And so that's why a lot of these modified gravity theories are disfavored, because they tend to be a little bit more on the complicated side. And whereas particle dark matter kind of it's pretty simple and can be used to explain a bunch of things at once. On that score, particle dark matter is, a highly favorable candidate to explain the signatures that we see in the cosmos.
So it seems like dark matter is the best explanation we have for what's going on in our universe. It answers a lot of different questions at once. But I don't know. Even when talking to Joe, it was still kind of hard to imagine. Okay, so assuming dark matter is like particle matter, like, is it like everywhere the way matter is? Or is it like, could it, am I made of dark matter?
So that's, I've never actually gotten that question. It's a very good question. So like, we wouldn't have any sort of intrinsic dark matter component in us, because dark matter, at least the nature of what we expect it to be, something that is incredibly weakly interacting. So it doesn't interact with light at all, virtually at all. It's very unlikely that it would interact through the strong nuclear force. And that leaves just gravity. And when you're talking about gravity can't keep things bound up in objects the size of you and me. So we exert we exert a gravitational pull, but it's tiny. And so that's why it's not going to be part of us. However, within every given cubic centimeter around you, there's 0.3 grams of dark matter. And we're flying through space on Earth, which means that we're flying through like a cloud of galactic dark matter. So you could maybe make the argument that at any given time, there is maybe 25% of, maybe not 25%, but there's going to be some component of dark matter that's in you at any given time, by virtue of the fact of you passing through it. Like this, this ghostly wind that's passing through the walls of your room and everything around you, like it's nothing, but it's there all the time. And we actually call that the dark matter wind.
There are several projects spanning all over the world focused on finding dark matter. Many are based on the theory that dark matter is made up of WIMPs, or weakly interacting massive particles. And that's massive as in made of mass, not really as in big. So based on this theory, it should be possible that dark matter particles could interact with something, just very weakly. And to prove this, you would need an extremely sensitive detection system. Detection systems like this exist all over the world. And that brings me back to Italy, where I traveled to see one for myself.
Oh, that was scary. Ladies and gentlemen, once again, you're all very welcome aboard the Ryanair flight to Pescara.
So I flew from London to Pescara, Italy. It's a lovely little beach town, perfect for a quiet holiday, which is what I promised my friend Miranda when I dragged her along with me.
Yes, it is recording. It is recording, Mary. I'm telling you it's recording.
But the Laboratory Nazionale del Gran Sasso is in Gran Sasso, which is about 100 miles inland. So we got a car.
Amazing. So nice. This is gorgeous. I'm so excited. So
we drove.
Like, what is this mountain range called?
And drove.
I don't know if that's part of the Gran Sasso National Park, but I don't know what the mountains are.
Oh, is this not?
Hit
that not part
a
of
few
the park?
road bumps.
Miranda, I think it's closed.
No, there's no way.
Yeah, they're doing like construction up. Look. Yeah, I think we're gonna. I don't Oh no.
And finally, after about 3 hours of weaving through the mountains of Abruzzo,
There's no one up ahead that we can talk
we
to.
made it to a long
Maybe
tunnel.
I'll ask.
It took a good 5 minutes to get through the whole thing.
We're out! Ah! Are we?
Yeah, I see the light.
Oh, nice.
But once we made it through, we saw it. Well, actually, we passed by it the first time and had to turn around, but then there it was.
Okay, great.
Yeah.
It was more inconspicuous than I thought it would be, especially knowing how big the lab actually is. It's very flat, as if not to overwhelm the mountains that it's nestled in.
Sergi? I don't know. Laboratory Gran Sasso, there it is.
Yeah, that's you.
Oh, wow. Ciao, I have a meeting with Dr. Messina.
Marcello Messina.
I traded the security guards my passport for a few pamphlets and a badge,
Mettila là un attimo.
and waited
Over there?
for...
Welcome to Gran Sasso
Thank
Laboratory.
you so much. It's beautiful up here.
Yeah, it's a nice place, I must say. Yeah.
Dr. Marcello Messina, Senior Scientist and Technical Coordinator at LNGS. He's the one I came to talk to.
I guess
He's graciously agreed to let me pick his brain and show me around the lab.
You see all the
After lunch, Dr. Messina and I waited for a shuttle that would take us down to the underground portion of the lab. It's very unique that we're able to drive into the lab, although it does take a while. It's about a 10-kilometer drive. We have to go back through that long tunnel me and Miranda drove in through. And then through another tunnel, which only authorized vehicles have access to. The lab looked exactly how you would imagine an underground lab to look, complete with the echoey soundscape and water dripping from the ceiling.
They built this cavern. They discovered there was a big natural storage of water. There was a lake above the cavern. That's of course got empty when they built the cavern, but then
I was very aware that I was deep inside a mountain. I was handed a hard hat and told to make sure it fit snugly. And then we started our walk through the massive hallways. Massive as in big. There were 3 main halls, each with its own experiment. But the one I'm most interested in is the Xenon project. The hallway that contains the Xenon project has this big glass case. There's offices in it and tons of really impressive looking scientific equipment. I assumed this is where the experiment was taking place, but Dr. Messina informed me that that was just storage. The experiment actually takes place inside this also very large tank.
How much xenon is in there right now?
the instrumented one is 6 tons actually.
6 tons.
There's a banner hanging from it that diagrams exactly what's going on inside.
Our detector, you cannot see it, but you see the cryostat where the volume of xenon is contained. Cryostat is like the thermos where you keep...
But without it, you'd have no idea.
Coffee, cold or hot, depends what you... And so a double layer, the 2 cylinders, one into each other, you know. So
I stared at it.
In the middle of the 2 shells.
Kind of in awe.
You see what I call TPC, with star projection chamber.
I don't know what I was expecting, but it was impressive, the size of it. I'd come all this way to see this xenon, this very xenon that has been here for 10 plus years and could potentially be the thing that finds dark matter. Okay, so this is how the experiment works. Remember when Joe said that dark matter moved through the universe like a wind or a ghost? Well, the idea is that dark matter will pass through this particular tank of xenon, and that one of those dark matter particles, or WIMPs, will interact with the xenon particles. Now, xenon in particular is used because it's a pretty heavy element, density-wise, which would make an interaction with dark matter stronger than that with a lighter element. Noble gases are pretty reluctant to react. So this tank of purified liquid xenon acts like sort of a blank canvas. There are a lot fewer interactions than if it was, say, water, which sort of reacts to everything. But even with such a stable element like xenon, there are still going to be tons of interactions that aren't dark matter that need to be sorted out. This is the kind of work Dr. Joe McLaughlin is involved in, who I spoke to earlier. And it's also why liquid xenon experiments have to be underground.
So like looking for dark matter on the surface of the Earth would be like trying to listen for the drop of a pen at a Metallica concert.
Except it's not possible to have a truly blank canvas. You see, there's radiation everywhere. It comes from the sun, technology, it's even all over us. And all this radiation causes a lot of interactions with the xenon. It sort of creates all this noise that would make it hard to detect a weakly interacting massive particle, or the WIMPs. Even though the xenon is 1,400 meters underground, surrounded by water, gold, lead, some radiation still gets through all of that, but it's exponentially less than it would be if we were at sea level. LNGS has been conducting liquid xenon experiments for about 10 years. And even though they or any liquid xenon experiment hasn't found dark matter yet, that doesn't mean progress hasn't been made. All the work that's been done has contributed to a sort of exclusion plot. So all the time that they spend not finding dark matter helps to narrow down the parameters that dark matter could be found in. With every day, scientists are getting closer and closer to finding what they're looking for. And this isn't just one lab searching for dark matter. There are tanks of xenon all over the world, and everything they find or don't find, that helps the rest of the community. It's sort of a global effort. All over the world, scientists are investing incredible amounts of time and money looking extremely closely at a bunch of xenon, searching for invisible particles that might not even exist. And they've been doing this for years. People devote their careers to this. So why? Why have so many people invested so much time and resources and money to find something that might not even exist?
In order to understand the model of the universe, you need to know the parameters that affect the dark matter physics. So the mass of the particle, the abundance of these particles. This will allow us to understand more about our universe.
And of course, it's exciting to learn more things about the universe. But it seems like a long time to look at liquid xenon just to find something that might not even exist. What's the point? If dark matter is found tomorrow, what does that mean? Will it all have been worth it?
This is fundamental research.
Yeah.
Fundamental research is something that you cannot find a justification in the everyday life.
Right.
I mean, the understanding dark matter or Higgs boson or the mass of neutrinos, this will not change the life of anybody of us. The number that you get does not change our life. It's the effort to get this experiment measurements done that will change our life. Don't forget that there is no witness, absolutely, of any discovery in any field that was not the byproduct of a fundamental research. You never wake up in the morning and say, now I invent these things. The invention, anything that you can imagine, from electricity to all the diagnostic in medicine, whatever you can imagine, it's the accidental byproduct of fundamental research. This is the big justification of fundamental research.
With physics, especially particle physics, the research is kind of so far from the real-life practical applications, sometimes it's hard to see the purpose of it. But in reality, physics is everything. It's the basis on which so many discoveries and technology has been built.
Well, particle physics is also involved in cancer research, radiation therapy to treat cancer, right?
Yeah.
None of that would have happened if we hadn't been doing stuff with particle physics, if we hadn't been studying particle physics in the past, right? And there's also something called proton beam therapy, or sometimes called hadron therapy. And that's really useful for wanting to, irradiate, say, a tumor that's embedded deep within your tissue, right? And the fact is that this process, because it entirely depends on how much energy you shot the proton at in the first place, it's very tunable. So you can actually get a way of getting surgical precision at attacking a tumor without ever having to cut a person open for surgery, right? And that's something that comes from, that is a real, an active form of cancer treatment that comes from studying particle physics. So I'm kind of giving you general examples here, but then, as to, why we should study dark matter in particular, right? This comes back to the notion of dark matter is a piece of low-hanging fruit that can help us build better models of particle physics in the future. And again, you put those models in the hands of a clever engineer and you get stuff like proton beam therapy or radiotherapy or smoke detectors. Smoke detectors are highly, particle physics, or like they rely heavily on particle physics and quantum mechanics.
No way! So I guess the answer is we don't know. We don't know when we'll find dark matter. We don't know if we'll ever find it. And we don't know what the potential discovery of dark matter will do for society, for our planet. But what we do know is a whole lot more than Fritz Zwicky did in 1933. And that's kind of what science is all about. This podcast was written, edited, and produced by me, Mary Westover. Thank you so much to Dr. Marcello Messina and Dr. Joe McLaughlin for sharing their time and their thoughts with me. And thank you to Miranda Morrison for her moral and navigational support. See you next time.
Wow. I mean, just wow. What a great job. Thanks, Mary. I told you, everybody, what a great episode. If you know someone interested in the things we do around here in STS, just ask them to get in touch. Maybe it's to explore stories like this one. Or maybe they're interested in science communication and want to do more. Or maybe, just maybe, it's history and philosophy of science, like some of the ideas in play here in this episode. These all fit under the umbrella of Science and Technology Studies, or STS. We're a thriving community here at UCL, and there's always room for more. Music in my part of the show today was Rollin' at 5 by Kevin MacLeod. That's available online at filmmusic.io. Music used by Mary is listed in the show notes. WeAreSTS is the production of the Department of Science and Technology Studies at University College London. If you want to find out more about the show, listen to past episodes, or give us some feedback, just visit us online. Here's the address. It's ucl.ac.uk/STS/podcast. That's it for today. Thanks for listening. We'll have another episode ready soon. More student projects are on the way too. Until then, just remember, there's knowledge to be found just about everywhere, and together, we are STS. Bye now. You've been listening to We Are STS, a podcast from the Department of Science and Technology Studies at University College London. Subscribe to the show and join us online. The address, ucl.ac.uk/STS/podcast. Some of the ideas in play here in this episode. These all fit under the umbrella of Science and Technology Studies, or STS. We're a thriving community here at UCL, and there's always room for more. Music in my part of the show today was Rollin' at 5 by Kevin MacLeod. That's available online at filmmusic.io. Music used by Mary is listed in the show notes. WeAreSTS is the production of the Department of Science and Technology Studies at University College London. If you want to find out more about the show, listen to past episodes, or give us some feedback, just visit us online. Here's the address. It's ucl.ac.uk/STS/podcast. That's it for today. Thanks for listening. We'll have another episode ready soon. More student projects are on the way too. Until then, just remember, there's knowledge to be found just about everywhere, and together, we are STS. Bye now. You've been listening to We Are STS, a podcast from the Department of Science and Technology Studies at University College London. Subscribe to the show and join us online. The address, ucl.ac.uk/STS/podcast.